Okay, guys, I'm going to give you a quick overview to Lab 6, series circuits. In Lab 6, I've used the Cook Labs 12 and 13, exercise 12 and 13. We're looking at troubleshooting series circuits as part of Lab 12, and Lab 13 is the series circuit voltage division. The purpose of both of these exercises is to illustrate Kirchhoff's current law and Kirchhoff's voltage laws in their application to series circuits. So open each lab link up and read through the lab parameters. I'm going to first look here at lab 12. We're essentially setting up a simple series circuit that has two resistors, both of them are 120 ohms, and a light bulb. And in this circuit, we are infusing some problems. We're going to create a short circuit and observe what happens. We're going to create a open circuit as well and observe what happens. Then you need to document your observations on the answer sheet back here at the end of the document itself. So to do this lab, you may either use the electronic circuits applet or you can use Tinkercad. So here I've pulled up the electronic circuits applet and I went and set up the basic circuit that was illustrated in lab 12, exercise 12 there. We have a source voltage of 18 volts. I have to right click on that battery and change that to 18 volts. We have two resistors. Now it calls for two 120 ohm resistors. One of the downsides to this applet, it doesn't allow us to place resistors bigger than 100 ohms. So I take that 10-fold off and I made them two 12 ohm resistors. So I have a 12 ohm resistor here, 12 ohm resistor here. I pull the light bulb out and hook that up, and I just connected the wires. And here is our circuit in its normal operation. Looking at our source voltage with a voltmeter here, if I put the positive probe of the voltmeter on the positive end and the negative probe of the voltmeter on the negative end of my battery, I'm reading 18 volts. That's my source voltage. Kirchhoff's voltage law says that the sum of the voltage drops equals the voltage applied to the circuit itself. So what I should be able to see is if I add each of these voltage drops, so resistor 1, I see 6.353. And if I came around here and added my light bulb in here, now I'm at 11.647. And then I come and complete my circuit adding this other resistor in here, I'm at the total applied of 18 volts. So each element has its own voltage drop. That resistor 6.353. My light bulb, if I were to look solely at the light bulb, has 5.294. The sum of the voltage drops equals the applied voltage. Now, Kirchhoff's current law says that in a series circuit, there's a single path for electrons to flow on. You can see that very visually here in this applet. One pathway for electrons to flow on, which means that all our electrons have to pass through each and every element here. So a very simple problem that circuits will have is what's called an open. Maybe there's a cut or a nick in a wire and it causes a problem in the circuit itself. So let's simulate that. We're going to take this wire right here and I'm just simply going to delete it. Okay, obviously a very clear problem is visual here, but if that was a cut and a nick in a wire and it looked like it was all attached, the circuit wasn't working, now I have to go around and figure out what's going on. You notice my voltmeter, which was across the light bulb, now says 0 volts and my light is off. In trying to troubleshoot this, I start here at my source and my source says there's 18 volts there. I can take a look at each of my elements here. Again, there's 0 volts on my resistor, and there'll be 0 volts on my on this resistor here, and we saw 0 volts at the light bulb. How can I find out what the problem itself is? Well, the indicator that there's 0 volts says there's no current flowing, and I have a good hunch that it probably is an open circuit. I can use my voltmeter and I can work my way around the circuit. What I'm going to see is once I find that open spot, whether it's on a wire or a component, once I bridge the gap of that open spot, I'm going to see all of the source voltage right at that point. So on an open circuit in series, I can use a voltmeter and I can locate where that problem area is. Now, very obvious to us here because we can see the open gap, but imagine this to be a nicked or cut wire that we couldn't see, and I'd have to probe it around. I can use a voltmeter to find that very common problem that is often experienced in troubleshooting series circuits. Now, in exercise 12, you're going to be asked to create another very common problem, a much more dangerous problem experienced in electric circuits called the short. The short is essentially a shortcut that does not have a load on it, and it can cause severe problems in circuits, including leading to fire, because it leads to an overcurrent pathway. So to simulate the short, you're going to be asked to do a couple things. One thing you're going to do is you're going to short the resistor. So I'm going to take this wire here and this wire here. We're going to touch those two things together. I'll move my probes out of the way just so you can see. Notice the electrons sped up just a little bit, and you saw the light bulb got a little bit brighter in this. If I took my my probes here, again, we see we start with a source voltage of 18, but as I go around, notice that that my resistor over here is going to have a larger resistance voltage drop of 9.818, and when I look at my light bulb, it has 8.18. The sum of these two equals pretty much the applied voltage, which means there's essentially 0 volts over here at this resistor, and we can see that by probing that. So that resistor has 0 volts to it, and we know that that is where our problem is. That's where our shorter component is. So putting together the idea that the light got brighter and our voltage drops are not the correct calculated values, we've indicated that there is a short. As I probe around here, I find the 0 volt mark over this one. I know that this one is the one that's been shorted out. Now, if that short were across the light bulb as a component, I should have left that wire there. I just take this here and I short the light bulb out. The light bulb very obviously goes out. Obviously, there is a problem there, but the circuit itself continues to function. Again, we're going to observe some very similar parameters or similar observations. This time, we have 9 volts at that resistor, and if you guessed it, we got the same value resistor. So over here, we're also going to see 9 volts. 9 volts plus 9 volts equals our applied 18 volts. When we go and probe the light bulb itself, we have 0 volts there. So knowing that the light bulb is out and it has 0 volts on it, and knowing that my two resistors have unusually high voltage drops to them and they split it, I can conclude that the light bulb itself is shorted. And the dangerous end of the short circuit is if the source were to become shorted. So here we are back to normal, and if this happens, we have a very severe problem. I'm going to short the source out by putting this wire between here. So when I let go, so our light bulb went out, and notice they simulate a fire here because there's no load on the circuit. Every circuit needs a source, a pathway, and it needs something to convert that electrical energy. When it doesn't exist, when that load doesn't exist, this shortcut is a rapid current discharge of the battery that leads to overload and burning the component up. Very similar to what you saw in Lab 9 in the smoke theory there. We got too much current running through there, causing too much heat, and that's going to burn things up, and it's going to cause big problems later on. If you choose to, you can model exercise 12 in Tinkercad. Pull breadboard out, pull your components out. I have my two resistors here. You're going to want to set those resistors, that resistor value to 120 ohms. And you want to make sure you have them set up in series. So here I have my power supply going to the positive bus line on the board here, my resistor, and then my wire to my light. And then from my light, I go to my other resistor, and I'm back to the negative bus line over here. I've pulled out 3 multimeters that have turned into voltmeters, and I've wired those across each resistor and across the lamp itself. So when I start the simulation here, I can set my power supply to the 18 volts that's requested in the circuit itself. So here we are at 18 volts. Now I got a slightly different type of light bulb here than I did in the circuit applet. So we got slightly different values, but we do see the very similar results. 7.5 volts across the resistor. Of each resistor, same value. Also remember we're using a 12 ohm resistor on the other circuit too. So it's 120 ohms here. And a 3 volt drop across my bulb. I can simulate those same problems of open and close circuits, and I could also short my bulb out. For example, if I inputted a wire right here, so I'll just stop my simulation for a moment. I'll put a wire in there, and then I start the simulation. Notice the light is out, and I have the split voltage drop across my resistors. Same experience that we had before, and we have 0 volts there. So this is an alternative way of doing exercise 12. Either way is acceptable. When you're finished setting the lab up, use the snipping tool to take a photo of your lab to put that in your lab report. Now in exercise 13 of lab 6, we're specifically looking at that aspect of Kirchhoff's voltage law where we have the sum of the voltage drops equals the applied voltage. The fact that current is a constant value in our circuit is important to understand. What we're essentially looking for is 3 resistors that are going to create different voltage drops, a 2 volt, an 8 volt, and a 15 volt drop when the source voltage is 25 volts. So read this through carefully. Look at the schematic. Notice what they've given us. We have a power supply of 25 volts. We have a resistor 1, they tell us is 120 ohms and is going to have a 2 volt drop on it. When I look at between test points 1 and 2, they want an 8 volt drop on resistor 2 between test points 2 and 3. And they want a 15 volt drop when we look at resistor 3 between test points 3 and 4. The sum of these equals 25 volts. What we don't know is what is the value of that resistor. That is what you have to figure out. Figure out what the value of these resistors are and build your circuit from there. You need to start putting together Ohm's law, Kirchhoff's law, and figure some stuff out. Here they give us 120 ohms and 2 volts. Use Ohm's law, figure out what the current is. Kirchhoff's current law says it's a constant through here. So the current at resistor 1 is also the current at resistor 2 and the current at resistor 3. Using those values, you should be able to calculate the approximate resistor value that would go in place here. Now, just a side note, you're going to calculate a fairly exact value. You're not going to be able to find that in standard stocks of resistors. So you're going to have to approximate a close to value when you're looking at that. After you've figured out what the circuit design looks like, you're going to need to complete this chart here. Tell us what the calculated resistance is, and then tell us what the standard value would be. Don't forget to fill out what the current is in milliamps across the top here for each of our resistors. And then what are the measured voltage drops at each of them, and how close are they to the predicted or desired voltage drop. Then look at the sum of 2 voltage drops between test points 1 and 3 and between test points 2 and 4, and fill this in the chart here, and complete the rest of the answer sheet here. In order to do this particular lab, you must use Tinkercad. So the Tinkercad circuit is going to look very similar to this one right here. You're going to have to figure out what those resistors are. I've taken the power supply, put it on the bus line. I wire up my resistor in series. So I have them in series on this proto board here. And then I have 3 voltmeters here so I can look at the voltage over each of them. When I start this simulation, make sure you have 25 volts applied. Now notice these are not the exact drops, and this is not the solution to the problem. I'm off by 1 here. I'm making my changes, but it is fairly close, and so you have to make some calculations. You're going to record this both in the table and chart, and then I want you to build this here and use your snipping tool to document that for your lab report. Okay, good luck.